questions that way. Okay, thank you very much for attending my talk on determining uranium geochemistry within natural organic matter environments, or characterizing uranium within organic matter rich sediments using X-ray techniques. So why do we study uranium? I'll start with uranium was discovered in 1789, named after the recently discovered planet Uranus. But previously it had been a mysterious mineral that had been discovered at the end of silver mines, which was colloquially called pitchblende, and that has stuck today. Well, as you know, for economic reasons, it's radioactive by natural decay, but it's also fissionable and fusionable. Was primarily researched and made into weapons, bombs, tanks, and munition. But nowadays, energy is the main use of uranium and is a raw ingredient for nuclear power, whereby 10% of the world's electricity comes from nuclear power. In the environment, obviously it's radioactive in that it's harmful, but it's also toxic, with the target organs being the kidneys. In as far as isotopes go, there are three main naturally occurring isotopes. There are more man-made ones, but natural uranium consists of 99% 238, 0.7% 235, and a small amount of 234. 234 is the most radioactive. 235 is fissile, and that is the main ingredient for nuclear energy and weapons. But obviously there's a small amount. So natural uranium is enriched, and to get rid of the 238, and when you separate the two, that's then depleted uranium, or DU. Other uses of the decay chain and isotopes are in dating rocks. So using the ends of the decay chains, where uranium naturally goes to lead, but uranium-lead, uranium-thorium isotope ratios are used for dating things like speleotherms, which tells us about our climatic record. Geochemistry, which is the focus of my work and today's talk. So in the environment, there are two main oxidation states we're interested in: the reduced stage, uranium-4, and uranium-6. We do have a uranium-5, which is an intermediary, but it's pretty hard to detect and work with. So for the purposes of detection techniques, I'm going to apologize and leave that out of today's talk. But we're concerned with solubility and mobility. Uranium exists as oxides in the U4 and 2+ state as U6. And it's useful to understand mining, exploration, and the environment. In determination, we can find out the oxidation state using chemical leaching by means of hydrogen carbonate chemicals, or we can look at X-ray techniques like XPS, XAS, and XRD. So just a quick slide here showing the world usage of nuclear power. The top 3 consumers of uranium are the USA, France, and China. But the top 3 producers are Kazakhstan, Canada, and Australia. Kazakhstan and Australia do not currently have any working nuclear reactors. Australia has a research reactor, and the Olympic Dam has the highest resource, as a co-product mine with copper, has the highest resource of uranium in the world. That's all run, so there's 439 operational plants requiring a total U of 68,000 tons, and those figures are correct of 2019. So uranium is part of what they call the nuclear fuel cycle, and the cycle because it does close the loop. So it starts off with mining, and the picture at the bottom of your screen is the picture of Ranger mine in the Northern Territories in Australia. That mine was an open cast mine. It's pretty much been packed up now and infilled and rehabilitated. But BHP have the Olympic Dam in South Australia, and that picture's the picture of their processing plant. So we go from mining to processing, and they're extracting the uranium from the ganga by maybe flotation. You end up with a product called yellow cake, which is the exportable uranium form. So that yellow cake is then converted and enriched as uranium hexafluoride, and enriched to get rid of the 238, and is turned into 235, and that's done by centrifugation. When that is processed, that then becomes your fuel rods, which forms the power source of nuclear power plants. That stays in there until the rods are cool enough and not producing enough heat, and then they sit in cooling ponds. So to complete the cycle, at the bottom there, these are put into storage as spent fuel storage, and then there's high-level waste, low-level waste from different parts of the process in the plant and decommissioning. And what we're really concerned is the next part of how that gets into the environment. In mining, that might be tailings, there might be leaching from storage of waste. We don't know, that's why I've put a question mark there, it's too new. And leaching from tanks where it's being stored, and of course accidents from nuclear power plants. So naturally in the Earth's crust is, as I say, it's ubiquitous, so it's 1 to 3 ppm in the crust. Seawater is about 3 ppb, groundwater a bit higher than that, tens to hundreds of ppb. Then you have various different concentrations in rocks, granites being quite significant and sometimes radioactive, and then black shales and phosphate rocks quite high, which can be a concern if it's used for fertilizers. And then you've got Olympic Dam breckers and dacoita lignites, and that can show considerable concentration of uranium. So why are we concerned with mobility? It's important for deposit formation and for following contamination. In deposit formation, the typical type of deposit you would get across is the roll front deposit, and this is a redox front where uranium-6 comes in through sandstone in groundwater, hits a redox front, becomes reduced. Often there's some sort of iron sulfide or pyrite, maybe bacteria there at the front. So that's that picture at the top there, that was an open face, and the image below in the explanation. We're also interested in waste. The other type of deposit is a sedimentary type of deposit where uranium is co-accumulated as the sediments form and fall down. And we'll go into more detail on solubility and mobility, but will depend on your U6 and U4 oxidation states. So uranium 4 is comes from something like weathering of granitic rocks, and once that's been oxidized, uranium-6 is then mobile through the environment, or is static and can form secondary minerals. No, it quite likes other ligands such as carbonates, phosphates, sulfates, silicates, vanidates, and hydroxyls. These have different affinities with uranium. So with the most important one here being the carbonate affinity, which is soluble as well as highly competitive. Phosphates are less soluble and maybe deposit forming, and also quite important. But other factors that come into it are oxidation state and pH, as previously stated. So as far as the geometry of the zanes is considered, the main differences in the zanes between the reduced uranium-4 and the oxidized uranium-6, apart from the position of the edge, is the uranyl double bonded shoulder that is apparent here, and this is because of the double bonds to uranium, which there are no double bonds in the uranium-4 compound. And oxygen also hosts a ring of many other oxygens in a sort of hexagonal plane. So why uranium has a particular affinity as well as inorganic ligands. It has an affinity for organic ligands, and this is an example of humic and fulvic acids, which are breakdown of plants, and they have functional groups, quite a number of ones, but the main ones we're really concerned with are the phenolic, the OH groups there, and the carboxyl groups, which can bind onto metals and perhaps uranium. Now in 1964, a guy called Strathclyde was probably a pioneer in noticing that when he measured groundwater entering a wetland, that it was very low ppb, but when he looked at uranium within the wetland, it was very, very much higher, and he concluded that there was 10,000 times concentration of uranium from groundwater into the organic soup of the wetland, concluding that UO2 attaches to humics, but no one is able to really prove that at that point. So as far as deposit forming goes, wetlands go through a cycle which takes between thousands of years and millennia, and they would eventually dry up, sediment, form ground, and layers form on top, eventually forming sort of sedimentary seams. Now, if there's uranium in that, that would get trapped and concentrated. So we end up with, that would be a low crusting type deposit. So we end up with concentrations there that may or may not be mineable. Here is a map showing uranium resources in purple, that's inorganic and organic, and the yellow dots show where the organic deposits, the more famous ones, exist. There's a whole host in the Colorado Plateau. You've got Grant's uranium mine in New Mexico and up into Alaska in Canada. The most famous one is the Gabon deposit in Africa, and this was actually a natural fission deposit, although by the time it was discovered, that process had long gone finished. Unfortunately, it has now been mined, so chances of being able to study that deposit are less likely now. The deposit that I'm concerned with today and worked on a lot when I was in Australia is the Mulga rock deposit in Western Australia, which is sedimentary organic. Now, on the surface, it's not much to look at. because it's dry desert, but once that would have been a wetland with water draining from the northern mountains. So this was discovered in 1979 by Uranium Resources, and the estimated tonnage at that point was 65 megatons of U3O8. It was likely formed in the Eocene, so it was sedimentary and lustine. Looking at the generalized core lithology here, it sits over the top of claystone and between sand and siltstones, with more sand and sandstones on the top until you get to desert. The layer itself is very much rich in organics. It's high in uranium, low in pH, polymetallic. There are a lot of other elements, in fact, the whole periodic table, which actually was problematic because there was so much stuff in it. Also present are total rare earths in about the same concentration as uranium as well. But one of the, the main question about these layers was, well, what form was the uranium in? And to answer that, we had to engage in various techniques. So starting off with samples, I was given, presented with bulk, a number of powdered cores, which had been taken from the 2012 exploration program, and later also managed to get a preserved piece of lignite, which was encased in resin. Now this piece of lignite was really the lignite that just kept giving, because there was just so much in that small chunk of about 3 centimeters. So that had been sectioned and subsectioned into thin and mounted on quartz for analyses. So the techniques employed was laboratory micro-XRD with a GAD system. We had SEM, and then going to the synchrotron X-ray fluorescence microscopy, so that's a mapping technique, with also speciation capabilities, and of course standard XAS for oxidation states, speciation coordination with your zones and XAS. So there's the Australian synchrotron. It's a 3 gigaelectron volt accelerator. At the time I was there doing the work, there were 9 beam lines, but now they're going through a BRIGHT program with increasing the number of capabilities of the beam lines. So it was built about 12 years ago. So just to give you some idea of the 2 beam lines I was using, the XAS beam line was running off a 1.9 Wiggler, and into a fast, it was upgraded while I was there into a fast DCM with 2 silicon selectors on it, 111 and 311, liquid nitrogen cooled. Moving into the experimental end station and hut, we had a 100 element uranium fluorescent detector filled with liquid nitrogen, and a cooling in sample helium cooled cryo environment for sample analyses, as well as your standard configuration of ion chambers and shutters. The cryo was particularly important for our samples because, being organic, they're highly friable. So this was able to keep the temperature down, the beam damage to minimal, and reduce the vibration of the analyses. For XFM beamline, the beam comes from an undulator off the ring, But the main things draw your attention to this one are the KB mirrors that focus the beam in the horizontal and vertical position, and the Maya detector. The beam is not focused for imaging, it is not focused for energy, so it uses the broad spectrum from about 2 to 18 or 20 kV. Now, more detail about the Maya detector, and I think there are a few more in the world, but there's one at DESI, and I think there's some elsewhere, but it's quite unique in some senses. So it's made up of 384 silicon detectors. The beam is channeled through the center of the detector, hits the sample, and then the backscatter fluorescence is detected on the other side by the silicon, and that goes off to be processed. Here it is the picture. This is a microscope lens to get your positioning of the sample. And the sample is mounted on very fast motors that enable fast scanning. And these are capable of analysing anything from a few millimeters to vast paintings, such as when they analysed the Decay painting to discover works of art that had been previously painted over. So a little bit more about XFM. It can do imaging and XANES, and it's controlled by a program called GeoPixie, which is developed by CSIRO. So what in the imaging sense is, what it does is collect the 385 spectra from the detector. You have a chance to reject any unusable spectra, and these are then manually merged into one spectrum. We do standard peak fitting from under the peaks, and when the peaks have been fitted correctly, they can then be used to process the raw data that's come in. And this is an example, not my sample, but we can get images from background, elastic, Compton scattering, etc., and the individual elements that have been identified from the spectrum. Now, to get XANES is somewhat similar, but in a different sense. So you are still imaging, but you're imaging at selected energies. Now, to get the XANES, you would collect, in my samples, it was, say, for example, 121 energies. So it would go from your pre-edge up over the edge, white line, and on further on, and these will be collected as energy images, and then GeoPixie will combine and stack these as image stacks, and to then connect the XANES, you would then extract regions of interest. So you can draw a box around your image and say, I want the XANES spectra from that, and then that would go off as an XY in energy and intensity, and then that can be exported to your standard XAS software such as Athena, normalized, aligned in the same way, and you would have analyzed some standards while you were at it, and to conduct linear combination fitting. I might add that this technique is not sensitive enough. The energy has not got the same energy resolution, so you can't do XAS, but you do get some good XANES spectra from that. So I was given these samples. Oh, so I can, if you like, pause for any questions at the moment.
Yes. So thank you, Susan. That was great. Actually, it was very interesting hearing about the sort of total geology of uranium. There is a question from Matthew Marcus. Why don't you go ahead, Matthew?
I was just wondering, Yeah, the diagram of XFM doesn't show a monochromator except for a multilayer, and yet you're getting Zane spectra. How do you do that?
They do have it. It does have a DCM.
Okay.
Yeah, but it's not as sophisticated as the XAS beamline one. So they can tune. It takes quite a lot of work. This is why it takes, and collecting a Zane spectrum from an image would, for example, take about, or at least when I did it, perhaps 8 to 12 hours, maybe, to collect a set of data rather than 20 minutes at XAS.
Oh, is it that it takes a long time to get from one energy to the next?
It does indeed, yeah. So, so there's I think more. I think they're much better and faster at doing. When I did it, it was, but it wasn't a routine technique. So it was a whole overnight process to do one sample. Yeah.
Right. They've been doing this for a while. That paper, the biosolids paper, has been out for quite a while.
Yeah. Yeah. So I think they're much better tuned now, but it's not a fast technique, but it's a spatial technique, which is very useful.
So I have a question. If anybody else has one coming up, please type it in the chat. I have a question, and perhaps the answer is you'll get to this in a bit. But in this concentration of uranium into the organics, is much known about whether that selects for isotope or for other way, or also selects for chemical forms? So prefers phosphate over carbonate or so on when it accumulates into these organics.
So I can answer the last question. There is definitely a preferential ligand exchange. So carbonate will preferentially latch onto uranium over phosphate, and some of the others are less preferential. There's a sort of competition for ligands. The organic matter one is less researched, so I haven't come across any isotope selection from that. Having said that, I think bacteria might be able to select for isotopes. It's certainly been shown with sulfur and pyrite, but again, I don't know in the uranium space what that's doing.
Okay. Well, so thanks. I don't see any more questions. So why don't you continue? And as people have more questions, they can type them in. Why don't you continue?
Yeah, continue. Okay.
Yes.
Stop. Right. So coming on to the samples and the analysis side of it, I was given a bunch of samples and asked to characterize them. The first sort of hurdle on that was I had the Geiger counter out, and it was, yes, I found the most radioactive one, but as I was sifting through it, it became less radioactive. But I managed to sort of pull out some of these smaller grains and take them to SEM. A lot of searching and find two bright phase particles, and of course only one of them is uranium. So really the question was, where is the uranium? And so that's just where the XFM really came in. So we took particles that were from the same pound and took them to XFM, scanned them. So this image shows, I think, 4 particles in the black box. And the results were astounding because one of them really shown up as being uranium rich, and others where you could see smaller particles in amongst other elements in the thing. So the first conclusion, yes, it was in the organic matter, and we can now see it using XFM, and it was very heterogeneous. And the heterogeneous is seemed to be the word of the year. And taking the same bulk cores to X-ray absorption, spectroscopy, beamline, we were able to do just sort of zones on those. And the conclusion was that the 70% of the uranium was uranium-6 and about 30 uranium-4. And in bulk comparison, that did line up with the chemical extractions that I'd been doing in the laboratory. So there's my sample there, for example. The lignite sample that I mentioned before had been subsectioned, and we've looked at various parts of this. And here, this image is the matrix of the piece that I was provided with, and that was the image. So no real features there. This is just a black hole, and yet when you look at it under with a uranium map, and you would see the same features if it was just uranium I've shown you here, but this is an RGB of yttrium, uranium and iron, and this corner was also a whole load of rare earths up here as well. And the fact you can see the features also indicated that uranium's right through the sample. And a few examinations of sort of the blebs show that other forms exist which are precipitated from solution, although I didn't quite identify, but that's probably a clay precipitation with uranium around the outside, or uranium phosphate. So we also did at the XAS beamline on these samples, took some XAS, and again on the bulk cores I had a few more this time, and there was an unmounted part of the lignite section with no features in it, and that's an SEM image of that with the bright phase being concentrated uranium, but there was uranium here as well. So on this sample, we just, not having a camera, took 6 random spectra at different places, and 3 came back, 3 were the same and oxidized, and 3 were the same and reduced. So we analysed these and compared them to the bulk cores. So there's the oxidized spectra at the top, and the reduced one showing the shells at the bottom. And I'll have to give credit. So I worked with Barbara Etchman to help. She did a lot of work in fitting these spectra. So the top 2, we see there is no uranium shell here, which you would normally get in this region. And this is all oxide, but we get a few small elements in this area, concluding that a uranium carbon compound could fit along here. Other features we observe are similar to that Melissa Denecki found when she was working with humics and uranium. So you get a broadening of the peak in about the same region. That's just a characteristic, and I'm not sure what that means. The reduced spectra, however, we see the hint of a uranium shell where it should be at 3.8 angstroms, and that on various trials fitted to best fitted to coffinite, which is uranium-4, but the silicate variation. So moving on, we also see features of pyrite within this lignite zone. As I said, this was a section that just kept giving. It had so many different features in it. So there was a lot of lignite, and around the lignite, we found these amazing uranium-rich rims Also present were arsenic and yttrium, but some really interest in the uranium, and a pyrite mixed with a sort of cobalt nickel millerite. So we took this to the, we took this back to the XFM, and we said, right, what's going on with the uranium? What form is it in? And the best we could do this was doing an image transect across the edge and trying to extract the zones from that. So this is what we end up with. So at the top, there's the image of, I'll start with uranium, sulfur, and iron, that makes up the pyrite, and the RGB at the top there. And then you see the uranium crust, very highly concentrated. This correlates to, and this is in weight percent, so a uranium peak here, and some other elements which on the same scale can't be shown. So drawing a grid across the top there, because that goes through a right angle and is perpendicular to the rim, I mean, we extract Zane spectra from these boxes that we draw, subject that to linear combination fitting using the end members that we had used. I mean, I tried it against both uraninite and coffinite, against uranopillite, 6th mineral. Some of these minerals I got from Melbourne Museum to look at. So we get a uranium-4 at the rim, which gradually goes into uranium-6 away from the rim. We get a little bit of uranium-6 in the pyrite as well. So we're asking the question, is pyrite driving the reduction? And although this has gone out to publication, it's still quite theoretical. Also had the chance to, in the laboratory, use micro XRD and drive a transect across a similar grain from another part of the sample into the pyrite. The pyrite's there with the uranium ring again around the outside. And so the scan was 1 millimeter. We used a 300 micron kilometer, which was overlapped. So we got 20 scans from that. With the first and last scans, there was a gradual transition. First and last scans with one being pyrite and the other fitted to coffinite, which agrees with some of the other data that's been produced. So I can summarize that so far. So we discovered that we have uranium in the organic matter. It's very heterogeneous. We have discrete particles, and we have diffuse associations within the organic sediments, and that might be bonded or just absorbed. We have uranium-6 oxidation states dominant within the organic matter, which challenges some of the previous theories that everything had to be in a deposit, had to be reduced. And we have the XAS indicating that there could be a binding to carbon there. With the rims around the pyrite, we get a change in oxidation state with more uranium-4 next to the edge of the pyrite. So that we can perhaps question whether uranium reduction is facilitated by pyrite. And the phase here was identified as coffinite and some uraninite present as well. So that's, I can pause again for questions if you like.
Yeah, thanks. That was wonderful. So I think Satish had a question. Satish, are you there?
No.
I'll ask for Satish. He typed in. Those were some very nice uranium Zanes and XFs you showed. Do you know what the concentrations were for those?
Oh, yes. So we had measured concentrations with ICP-MS, and across the whole range of samples, we got from like 4 ppm up to about 5,000 ppm, with one sample being 15,000 ppm, sorry. So, and those more concentrated samples were the ones we took to the beamline. We couldn't analyze the weak ones, but the average was about 500 ppm uranium.
Okay, great. Let's see, for other questions, Peter, Watts, you had a comment or a question? If you're there?
It was, hello, Susan. Thank you for the presentation. Hello.
Hello.
Thank you for the presentation. I just wanted to make a really quick comment about that with respect to isotope fractionation, that there is isotope fractionation with microbial reactions, at least. If you want to know more about it, Rislan Benyei Lakmani at EPF Lausanne is doing a lot of work at the moment on isotopic fractionation in uranium in environmental systems.
Oh, that's very interesting. Yeah, maybe we'll have to catch up on that.
Yeah, definitely.
Great. Are there more questions? Let's see. So I think Satish also wanted to know if the uranium, if you were distinguishing organic uranium or organically bound uranium based on the zanes alone, or were you just following oxidation states?
On the zanes, it was pretty hard to look at. The extended zanes was flat and featureless, so that was only when we sort of started looking at the XAS, and because we didn't see a number of shells continuing after the short zanes, we assumed that it was organic or could be organic or non-mineral. Some of the zanes matched, as I think I showed, matched very well to coffinite. It is a bit tricky, but the first wiggles are shorter, and the and obviously you don't get the shoulder in the zanes as you do in the non-mineral. Sorry, yeah, I'm getting confused, but yeah, they're less. They have less feature than the mineral ones, I think, is the short answer.
Right. Okay. Okay. So I think there aren't any more questions yet. So why don't you continue, and we'll take the rest of the questions for the whole talk at the end.
Okay. Right. I'll carry on. So the next part of the talk, I'm going to talk a little bit about microbes, but that's not my expertise. It was just to sort of show some features and then move on to a laboratory experiment that really backs up what I have just been saying. So that's there. No, we're going the wrong way. That's it. So as an introduction to microbes and biogeochemistry, microbes have been observed to reduce uranium, and I think the first really dominant paper that came out was the work by Suzuki et al. In 2000, and they exposed bacteria, rod-shaped bacteria, to uranium nitrate, I think it was, and reduction was evident to what was later in other publications described as a non-uraninite phase. So looked like uraninite, wasn't uraninite, didn't possess the second UU shell. And this was described as being direct enzymic reduction, and at the time the metallic, was it a metabolic process from internally within the bacteria, or was it all done outside through the secretions of the extracellular biomass? Or and it's likely that because uranium is toxic, it is unlikely to be the first choice that bacteria would process after the electron shuttling of that. So they would use up everything else in the vicinity before they would touch uranium. The types of bacteria or the groups of bacteria that have been shown capable of reducing uranium are iron reducers, such as Shigella, putrescens, passions, metal reducers, Shigella wanadescens, that's a general purpose metal processing, and also processes sulfur. And then we've got sulfur reducers, such as Geobacter, sulfur reducens. So there's quite a number of communities out there that are quite willing to have a go at uranium. So back to the lignite sample that just kept giving, one of the most striking features that we ever first saw at the surface was this vast expanse of uranium-dense ellipsoids, randomly orientated. This is an SEM image, map image, and showing them in the matrix. So further analysis, and you start to see some features. We took a fib sample out of one of these across this one, I believe, and another one from elsewhere, and that's them as a combined image there. And to TEM, looking at them more closely, I haven't quite got the room to show you, but we also took diffraction patterns and noticed that there were sort of 10 nanometer shapes within these structures. Taking this to XFM beamline, so at this point, I mean, this is pretty amazing. At this point, the fib samples on a copper grid, the copper grid's 3 millimeters wide in diameter, and we get this image from the skill. I have to hand it to the skill of the beamline scientists to do this. So we get the image, and it's mostly uranium with a bit of yttrium. I think we've discovered some other elements there, but they're immortalized with uranium. The diffraction patterns from the TEM aligned with coffinite rather than uraninite, and that sort of backs up what else we've done as well. So that when we did took the Zane stack images as previously described, ran a number of mineral samples at the same time, and with linear combination fitting was much more similar to coffinite than with uraninite, just from the distances of these shells, and it was definitely reduced. There's no shoulder here, whereas you can see a shoulder on the uranophane, which is a uranium sulfate mineral, and was quite exciting, really. So that sort of wraps that up. We tried to sort of think about the theory of this further, but so kind of really stopped there on that little project. But what I was able to do next, after all those analyses, was to design an experiment to ask the question, how did mobile uranium nitrate behave with solid organic matter? A lot of work previously had been using soluble organic matter, such as humics and eufulvic acids, because they're sort of available from the IHSS for research, but less had been done with solid, in mobile matter. Now, what I really wanted to do was get hold of some peat. Now, peat's quite a rare commodity in Australia, So I looked a bit further as to what could be my surrogate organic matter, and there it was staring me in the face. Eucalyptus bark, Eucalyptus globulus, and there's the tree that I took the samples from on campus, is the main species that is used for oil production. So took that, ground it up, and sieved to the same, and conducted an experiment in columns, passing uranium through the columns, and with sand as my control, and tree bark and sand as the focus. I mixed tree bark with the sand to help the flow of the solution through, because without it, it didn't flow very well at all. And then I took these columns in duplicate and ran it through a whole host of analyses, including XFM and XAS. So here's my schematic of my setup. So I could run water or uranium or salt through as a tracer. We had cotton wool to stop the material moving, glass columns, and then that was the outflow was detected by electrical conductivity and pH and ORP, which went to a data logger. Then that went on to become to a fraction collector, and that went to ICP-MS for detail concentration. And I did this in replicates, so that was split longitudinally and horizontally in cross section. And there's my setup with the data logger, the pump. This is just plain solution at the moment, salt solution. I added, so it got more complicated basically with adding the fraction collector and the uranium solutions afterwards, but that's probably easier to see it more simply. And then behind there are my probes detecting the outflow. So the results came back, basically the dotted line is my tracer, which I ran through first, and the solid line is the uranium solution detected by EC. And the solution went through faster through the sand and much slower through the tree bark and sand. So that was all very well, but when we looked at the actual concentration in the fractions, uranium is still present in ppm levels, in milligrams per litre, but we get almost nothing coming through from the tree bark. I ran this experiment much longer than 2.5 hours. It went on for 6 or 7 hours, but that's the interesting part of the spectra. When I came to dissecting these columns, so this is first in cross section, scooped it out. No more dots here because lost some of the column. So this is from handheld XRF, looking at, and here we get an even distribution of uranium about the similar type of ppm. However, we look at the tree bark and sand column, and I think it even goes off the scale much higher here from the first sample. We get only uranium to about 7 centimeters and then nothing, or very low amounts. And I was able to collect other data as well at the same time. And there was calcium provided a negative correlation with uranium at this point. Calcium is very dominant in plants. It helps form the structure of the plant, and it's also a divalent cation, similar to uranium. So interestingly, perhaps we can think that there might have been a cation exchange going on, helping uranium to absorb very rapidly at the start of the column. So we split the column longitudinally, preserved it in resin, took it to XFM beam line to scan the length of it, and here are the first parts of sections of those columns. This is hot because that's the cotton wool, and this has lost its cotton wool for this sample. In the sand, I'll talk you through the sand column. Uranium is present throughout the column. You can see the circles of the sand particles, which are roughly spherical. And we look in more detail, and a few hot ones here and there, and again under the colour map. In the tree bark, it's a different story. We get a concentration right at the beginning of the column, and this is tree bark this time, and this forms a sort of preferential flow where the water's flowed, the solution has flowed through carrying the uranium, and then we get nothing. On increasing the resolution, we see that okay, sorry, I'll state that XFM is invisible to carbon because it's too light an element to see. So we can use surrogates like calcium, or the shape of the tree bark is splinter size. And again, so this is all uranium where it's green. And on higher resolution, again, looking at this part, we see uranium in the splinter shapes, the rod shapes, and calcium. Calcium's only visible at the very surface of the sample because of the attenuation of the beam. Uranium is picked up much deeper into the sample, but calcium can only fluoresce the X-rays from the surface. So that's why you see that, but there are no elemental associations here. In higher detail in SEM, this is particles of uranium and, sorry, this is particles of the quartz sand and the tree bark together. We don't, where this is, we don't see any round, oh yes, that's a good point. We don't see, and there's sand present in this sample, and we see no spherical particles at all in the uranium shaped. And this is important. So it's attached to the bark. On another part of the sample, we see it's attached around what looks like the vascular tissue of the plant. There's no uranium on the sand particles. That bright phase is iron, which is common on sand, but not uranium. So we get a preferential absorption. This was actually agreed with a model I ran through using the WAM6, and putting in the same criteria. We see that it also attached to the solid organic matter and not to the sand where that was present, and that was due to the charge of the particles. So with the organic matter being more heavily charged than the sand. This, of course, I also examined all the dissected columns at 1 centimetre apart, ground them up, took them to XAS beamline, and they all look the same, basically. So that was uranium 6, so your uranyl nitrate, the same as what we put in, compared to a uraninite end member. And they all show the uranium 6 shoulder. They're the same shape as the uranium nitrate. So the conclusion is there was absorption but no oxidation state change. And this backs up what we see in the ancient sediments as well. So in summary of this particle, we get very rapid absorption to tree bark, which helps explains the heterogeneity of the the samples of the columns. It's possible that's through a cation exchange mechanism. There's no reduction to uranium-4 here. So that, as I say, that might help explain what was going on at Mulga Rock. But also, could we use tree bark as a potential absorbent to clear up mobilised uranium spills, uranium-6 spills? And putting that together into a Mulga Rock conceptual model, again, we've got uranium-6 in low concentrations in the groundwater, getting rapidly absorbed to organic matter. Where that has occurred to orthogenic pyrite, we might get a reduction around the edge, and where that has occurred near bacteria, they might have reduced or helped reduce that to coffinite. I might say that the coffinite is, yeah, it's a silica rich, and other organic deposits have also noted coffinite as opposed to uraninite there. Not only that, we get precipitates of other sort of salty minerals occurring within the organic matter. So we've got molecules, minerals, and microbes helping form the deposit. In summary, and future research, what I didn't really touch on was, so some of this we've already said. What I didn't really touch on was the lack of sulfur data that we have to explain some of the processes going on, which wasn't available to me at the time of analyses. And also, it would be interesting to do some more microbial work with sulfur and pyrite, organic matter, and microbes. And I'd like to thank you very much for listening and attending. And as a whole, there's no way I could have done this work all by myself. So there's a whole load of people I need to thank in Australia, some of which have moved on. And I'd like to thank the University of Strathclyde for enabling me to carry on with this, albeit I'm now working at the other end of the nuclear fuel cycle in decommissioning. So I'll stop sharing now.
Well, so great. Thank you, Susan. That was fantastic. That was really interesting. The idea of using tree bark is inspiring. There are a few questions. I think we were going to start with a question from Richard. If you're ready to ask it, go ahead.
Yeah, thanks a lot. Also for the presentation. I was wondering, the Meyer detector has a large solid angle, and therefore different pixel will see the sample under different angles, which then of course can change the emission spectrum for inhomogeneous samples. And is this something you have to consider in your data?
Sorry, if I can recount the question, was that working at higher resolution across on the pixels? Can you repeat the question, please?
Sure. So I think so I wondered, there are different exiting paths for different pixels for the Meyer detector, which will change the emission spectrum, maybe more absorption in one pixel compared to the other pixel, which has a different angle. And this, ideally, you get rid of it by some kind of calculations. But I was wondering if this effect is so large that it needs to be considered, or if it can be ignored.
Okay, so the main pixels, the main active pixels in the Meyer detector are around the center. Frequently, the spectra collected at the four corners of the detector are weak and noisy. And you can see all of these spectra when you're processing the data, and you get an image of the detector as to where which are the best spectra collected. And it's very, you can, you have a lot to go through, but you can select or deselect those spectra and not include them in your analyses. Also, there is a tendency for spectra to slide a little bit, and they can be realigned. They can spend many hours aligning them all to the main sort of 18.2 kilovolt peak. I think it's its escape peak or the Compton peak. I'm not sure how related that is to intensity. Certainly the ones in the middle are the spectrums are much sharper, as opposed to the other phenomenon you get, which is self-absorption. I think that's more to do with the sample. Does that answer your question?
Yes, thanks.
Okay, and I think Matthew Marcus had another question.
Yeah, it's about the, I was speculating that the non-uraninite phase might be perhaps an amorphous form, which would explain the loss of the UU shell. But Renee Bess points out that, that if there's lanthanides in it, that could explain it as well.
Right, so let's bring Renee in too. So Renee, you had a similar comment, or you want to expand on that?
Yeah, actually, did you observe lanthanide in the non-uraninite sample?
Lanthanite, no.
I mean, gadolinium or?
Any of the rare earths.
Oh, there's a whole host of rare earths, yes. I'm not sure that they interfere. But having said that, yttrium was one of the most dominant rare earths. I know it's not part of the lanthanide series, but yttrium was one of the dominant ones that seemed to follow uranium quite a lot. I didn't chase it. It was evident on a lot of the XFM scans. How that actually sort of relates with the chemistry gets incredibly complicated if you start pulling rare earths in there. They did extract, I did do some work, and there is a data set floating around where they all got extracted with the carbonate data set as well. But as to whether they are part of the shells, I can't really say. Part of the XAS. They're heavier elements, so they would have been perhaps more dominant than some of the lighter ones that we think we were seeing.
Okay, so yeah, I think Satish Manini had a question or a comment, and then we're gonna wrap it up to let people go onto other activities.
Yeah. Thank you, Matt. It's very nice talk. We actually did very similar study, like along the lines of what you did with the columns. So column 1, uranium-containing water flow. So we published this in 2008, which I listed in the chat button. So in a Journal of Environmental Engineering journal. So we looked at basically uranium-6 redox kinetics. But the Zanes, I mean, again, going back to what Matt was asking, or what I was trying to ask related to using uranium Zanes to identify the types of organic complexes that are playing an important role in uranium-6 chemistry. So yeah, we couldn't do that. And I'm wondering, using high energy resolution Zanes, we can actually get some idea on that. I mean, the type of ligands and the ligands that are participating in electron transfer, I think that would be pretty cool if we can do that.
Well, let me know if you can do it. My gut feeling when I was asking the same question was to go down the FTIR route to look for, and that would be a big project in itself. And it was one I was very tempted to do many times, but never had the time to do it. And that would be involving sort of mixing uranium compounds with a vast number of different organics. and then taking an FTIR spectrum for each of those and seeing where that sits. However, if you could do it with the zones, I would be very interested to see if that actually works as well. But
I mean, FTIR can give us, the chemistry of the total carbon, but not the carbon that is actually complexing with uranium. So I think a combination of ZANES or high energy resolution ZANES would be super. I don't know, maybe Matt or someone else can comment on that.
Well, I guess I would say that could be interesting. I don't know that I have an answer for that, but that's also a great place to allow people to disappear. So let's stop the recording and stop this. And thanks, Susan, virtually, and then we can continue on with those concepts in the future.